The broadcast is now starting. All attendees are in listen-only mode.
Hi there, welcome to our next webinar for this month. We have Jamie Surrette online here to run us through his battery webinar training. Jamie, thanks a lot for doing this once again. To all attendees, if you do want to ask questions, use your control panel, type the question in. We'll pause Jamie and ask the question for you. So thanks again, Jamie.
Okay, thanks Ed, and thanks everyone for attending. There's quite a bit of data in this presentation, so some of it we'll speed through, and in other spots, if you need clarification, as Ed mentioned, just ask for it to be paused and roll back, and we can maybe elaborate. But there are a few succinct points on charging in particular that I'd like to spend a good portion of the time on. So I'll kind of move quickly through the first and opening slides. First off, of course, just to give a quick background for those that don't know our company. Surrette Battery Company Limited was established in the late 30s in Salem, Massachusetts, and it moved to Spring Hill, Nova Scotia since 1959, and that's where it's remained since, where our production facility remains to this day. We market the product under both the Rolls and Surrette names. Rolls is becoming the predominant brand only because it's been marketed heavily internationally, but it's the same product. We currently, well, it's a bit of a typo here, but we are a deep cycle manufacturer with a very broad product range on the flooded side of 80 ampere hour to 3300 ampere hour. We've also been beta testing a line of flooded calcium product for over 14 months now with great success, and we have launched an AGM sealed battery program this summer. It's an ISO 9001 registered facility. Renewable energy represents about 50% of our production, and as you can see, we distribute this relatively broadly worldwide. So I'll click through some of these. A quick agenda, a quick note on the off-grid systems. They're really the only key here because I understand that everyone on the other side of this presentation recognizes how off-grid battery backup systems work, but the point to this is of course, if we don't size the batteries appropriately or don't configure the system to match up with the loads appropriately, the batteries don't work and the system doesn't work. And the only chemistry that we'll talk about today is quickly the discharge and recharging components. What I really want you to focus on is, as you can see, it's like metals. We've got lead, we've got lead oxide, and we have sulfuric acid as the electrolyte, which I'm sure all of you are familiar with. If you look on the right side, after we discharge the battery, we create lead sulfate. And the reason I want to point that out is because sulfation gets bantered around as this evil entity. And without the batteries creating lead sulfate, you can't pull energy. So sulfation is naturally occurring. So anytime you read that, it's impossible for this battery to sulfate because of a particular change in the chemistry, it's probably very doubtful. So sulfation occurs as soon as you discharge the battery. It becomes problematic later on, which we can talk about as this presentation continues. And as a result of most of you, hopefully, haven't seen the inside of many batteries, at least hopefully not as a result of an accident, I thought we'd just give you a quick idea of the cutaways of sort of what you're seeing inside the batteries. Both of our smaller Series 4000 and larger Series 5000, but the components are very similar. And just a close-up of actually the workhorse of any storage battery, deep cycle battery, is the positive plate, and where the negative typically is sacrificial in these applications. The positive does all the work, and it's the one that ends up getting protection of glass matting, envelope separators, and so forth. And traditionally, it should be much thicker, very dense active material, etc. And just sort of how the plates marry up to create a group. So capacity is based on the number, size, and the number of these plates that are included, and they're all welded together in a common bus bar or strap, as it's referred to in the industry. And all of these groups are actually welded robotically. And just continuing on, so you can actually get an idea of what the innards look like of these cells. And finally, from the top down, on any of our larger cells, the Series 5000, you'll notice that little arrow pointing to the positives. And it's just one more check that you can do on an inspection. Those arrows always should be pointing to the positives, and it's just one further indication you can make of polarity. But of course, you pick it up with your voltmeter as well. I won't belabor too much on this, but of course, capacity is one of the big questions of all of the customer requirements. You know, how much does this battery store when comparing across brands or across sizes? The capacity is measured in ampere hours. But one of the big things we always have to know is it's also determined by discharge rate. So when we refer to capacity, the thing that we have to keep straight is what discharge rate are we concerned with? Most renewable energy product is rated at the 100-hour rate given the long discharge periods, which means 460 ampere hour, S460 is our part number, but 460 ampere hour at the 100-hour rate actually means you can discharge that battery at 4.6 amps, 460 divided by 100, for 100 hours, from fully charged to fully discharged. However, if you're more concerned with a quicker discharge rating, i.e. the 20-hour rate, the same battery, it's not changed, same physical size, no change to acid densities, will provide 350 ampere hours at the 20-hour rate, or with a higher load, 17.5 amps, it can support that higher load for 20 hours from fully charged to fully discharged. The key is this relationship is not linear, and as the discharge rating decreases, so as you start discharging the batteries more quickly, the available capacity of the battery drops. So when sizing or speccing, it's very important that we make sure we're speccing the appropriate discharge rating. Capacity can be affected by various other things, but primarily the one we need to be concerned about is temperature. As the battery cools, its ability, because it's a chemical reaction to support loads, drops. So the reaction is slower, and its reaction is sped up or improved with heat. So in warmer environments, the batteries will actually perform better. The downside of warmer environments, of course, is it's harder to charge the batteries as the temperature increases, or the ambient temperature of the batteries increases. An idea of capacity versus temperature. Cycle life, of course, is another concern of most clients, which we're dealing with the amount of energy we're actually pulling from the battery. So how many cycles can we get? And the cycle life of any batteries is dependent on its construction, but it's also dependent on use. So the cycle life is really affected by the depths of discharge. So as we can see, this is for our larger cells, the Series 5000, roughly 3,200 cycles, 50% depth of discharge. However, you only remove 20% from the battery. You could actually cycle the batteries to 5,000 cycles. And conversely, if you ran the batteries flat, you would get fewer than 2,000 cycles, roughly 2,000 cycles at 80%. The key to all this is to get the most energy out of the battery over its useful life. Typically, around 50% maximum depth of discharge will provide you with the most energy over the useful life of the battery, and discharging below 20% allows you to actually charge the battery most efficiently as well. So how do we determine state of charge? With flooded product, it can be determined in two ways. It can be determined both by measuring specific gravity and by voltage. Now, specific gravity, or the measuring of the density of the acid, is very accurate on the discharge side, but on the recharge side, there is a bit of a lag depending on the size of the cell. The taller the cell, the longer the lag time, in order for the electrolyte to mix. Voltage can be very accurate, but traditionally, or technically speaking, voltage can only be done during open circuit. On-load voltage is very hard to measure. One of the issues of voltage being that open circuit is required, it's very easy to get false readings from voltage. If there's been a surge in demand on the battery or surge in current onto the battery, voltage might be suppressed because a pump has kicked in or a large load has occurred, like a vacuum or etc. That may suppress the voltage at that point in time. And conversely, if the batteries, of course, are on charge, if we push enough current into the batteries, we can artificially raise the voltage beyond their actual state of charge. So we have to be cautious when measuring voltage under loads. But if we're looking at state of charge versus strength of acid, this is available both online and in our solar battery user manual. And if we're looking at voltage, what we've done here is we've provided essentially a constant current. So we discharge the battery under a known current for a period of time, i.e. the 20-hour rate, and just measured voltage over that time. So roughly 50% is 1.93 volts per cell, or on a 48-volt system, roughly 46.3 volts. Now, if the rate of discharge was sped up, if the load increased, so instead of discharging at the 20-hour rate, we're discharging at maybe the 10, these numbers would actually be even lower. So it might be down in the 1.91 instead of 1.93. This is a good estimation, but that's all it is an estimation of the actual state of charge. It's great to corroborate back all of this data to the actual specific gravity readings. Now, this may seem quite persnickety. However, this next slide is actually proven to be very beneficial on preventing lots of difficulties that occur from battery banks that have gone into systems at partial state of charge. And if we think about the whole manufacturing, logistics, distribution matrix, if we're running at roughly 2 to 4 week lead times, product traditionally shouldn't be sitting on our shelves for any period of time. However, let's just say that it's the average period of time on our shelf is 2 to 3 weeks. There's probably another average of a week or two in transit, and then a week or two between dispatch before it gets to the dealer, and maybe they add a few more weeks before they put this battery into the system. The point to all of this is, although the battery left fresh from the factory or very close to its manufacturing date, it may be 2 or 3 months before it actually goes to install in the actual user's system. Now, in 3 months may actually be a very, very conservative number. During all this time, the battery is self-discharged, which is dependent on temperature. And if we were dealing in summer systems, summer installs, which is the most frequent, the temperatures, of course, are going to be the highest. All this to say, all the batteries act independently, which means every cell is going to have a slightly different voltage, and every battery, therefore, is going to have a slightly different voltage. And if we're dealing with a series string, the most efficient, of course, but often we're dealing with multiple parallel strings, so we just exacerbate all of these difficulties. The point to all of this is we install the battery bank, and even if you put the battery bank on charge right away, you will come up to whatever the bulk voltage is or the voltage setting is. But if you independently measure either battery or cell voltage, whatever you're able to do easily, you'll notice that even though you've reached the voltage settings, that independently or individually, cell voltages are going to vary. And early in the string, you're going to see very high voltages, and as the string lags or coming to the end of the string, you're going to see the voltages significantly suppressed. So if you're charging at 2.5 volts per cell, you may see 2.6, 2.65 at the beginning of the string and only 2.35 at the end. The problem there is we feel that the battery bank has now been fully charged, but it's not been balanced. And so in multiple parallel strings in particular, this is going to create significant imbalance as the client starts to use the system and starts creating even further imbalance as they discharge and recharge, because it's going to be difficult, very difficult to overcome the differences in state of charge. So one way around this, the best way around it, is to do an initial activation or initial balancing of the bank. So of course you need to check the polarity, measure the specific gravities of all the cells so that you get an idea of the state of charge, and measure the voltage, of course. And then they should be put on an initial charge. And you might as well go at a relatively high voltage to shorten the recharge period. And roughly 2.5, 2.6 volts per cell on the flooded cells, which would be the equivalent of an equalization. And you should maintain that, that charge rate until all of the voltage, again, between either the batteries or the cells, whatever you can measure easily, has become balanced. Moreover, if you inspect the liquid levels at the beginning, although they may be lower than you expect, if the batteries have been sitting, they will actually drop. So if the plates are covered, do not add water. And if they were low, notice the liquid levels after you've charged, and they probably will have risen dramatically by as much as possibly, you know, can even be as much as a centimeter and a half. And I guess, sorry, I should just pause to make sure that there are no questions on this long, drawn-out slide that I've just beat on. But I suspect Ed will stop me otherwise. So acid levels are the next question that often comes up. And what is the correct acid level? And again, here we're looking at roughly 1/4 inch below the vent well. And the vent well, when you remove the vent cap, is the little piece of plastic that slides down into the actual cell itself. The idea is you want to get as close to that vent well as possible without filling into the well. It is difficult to get exactly, of course, 1/4 inch, but you want it below the vent well so that when the batteries do charge, you don't end up with acid all over the tops and make a mess. And so next is into charging and looking at the traditional 3-step charge algorithm. As you can see, the blue line represents voltage, the black line represents current. And this is a 12-volt system, but just multiply by 2 or 4 depending on your voltage. And you'll see that they're pretty common set points. And just so we're all on the same page, you know, there's the bulk, absorb, and float stages of the 3-step algorithm, and of course the 4th step being equalize. What I wanted to point out with this slide, and for those of you who've seen this before, I apologize for belaboring it, but what I wanted to point out was firstly, the charge acceptance. Now this was a standard 220 ampere hour 8D that we manufactured. And if you'll notice, this is a flooded lead acid battery that's accepting roughly in excess of 20% of its rated 20-hour rate, while during its initial charge phase until the bulk voltage is attained. And so the initial current into the battery can be relatively high. The charge acceptance is relatively high until we attain bulk voltage. At bulk voltage, once it's reached, we estimate that the battery has attained 80% of capacity, or sorry, 80% state of charge. At the absorb stage now, we hold voltage at the bulk volt setting. So there's no change in voltage, but as you can see, the charge acceptance drops. And essentially because we have a peg voltage, we can't push any more current into the battery without allowing voltage to rise. And we're not allowing voltage to rise because we don't want to overcharge or overheat the battery. So voltage starts to drop until we drop into the float stage when current drops to negligible levels. The point to all of this is, how do we determine what the appropriate absorption settings are for the product? Because if we don't get the absorb stage correct, the batteries are always going to run into the next charge cycle, run into the next use cycle partially depleted, or will be deficit cycling. So how do we calculate what the appropriate absorb stage calculation is? So firstly, we need to know what the size of the battery bank is. Pretty easy, and in this case, always use the 20-hour rate. We know that we assume that the battery has reached 80% state of charge, so we're at a 20% deficit when we reached bulk voltage. So now we just need to calculate what's required. So 20% of our for this example, 350 amp hour means we need to put 70 ampere hours back into the battery. But to get 70 ampere hours back in, of course, we have to create or generate more as a result of inefficiencies. So 15% is a good factor to increase the required amp hours by. And now we need to divide by the charge rate. And the key here is, what charge rate do we use? We can't use the maximum charge rate, and we can't use the minimum current going into the battery during the absorb stage. We really need to use the average, which is difficult sometimes to determine. So unless you can view your current going into the battery easily and get an idea of what that current number is going to be, the better alternative is to sort of have the output of the charger. And with that, we end up with an absorb time. And in this case, based on a 40 amp charger and a 350 amp hour battery bank, we'd be looking at roughly 4 hours absorb time. Now, this is just a hypothetical example, but the reason we show it is to indicate that, generally speaking, the majority of the inverter chargers on the market have a preset absorb time of somewhere between 1 to 2 hours. And quite frequently, that is too short an absorb time for most battery banks being installed in off-grid systems. And if they're left at the presets, and the idea behind it is very valid, that way that the charger is not going to overcharge batteries unnecessarily or accidentally. But if they're left at the presets, you're going to result in batteries that are chronically undercharged, which means we're going to have to run more equalization cycles and or have sulfated battery banks that fail prematurely as a result of deficit cycling, sulfation, lack of capacity. So quickly, sorry for everything being off skew slightly, just a run through of the traditional voltage settings, but I don't want to spend a lot of time on this given that the majority or all of these data is available both online and in the solar manual, which rolls into what happens with batteries that are deficit cycled or left in partial states of discharge. So the plate on the left, as you can see, few flecks of white in it. This is a well-formed plate or a well-charged plate. There isn't much sulfation. Most people ask for these images because they want to know what actually sulfation would look like. Hopefully they're not tearing batteries apart, but here's an illustration. On the right, we see the hardened sulfation crystals that have formed, which all of that white space is available capacity that can't be used. So, a quick estimation would be roughly 50% of that plate has been, or 50% of the capacity of that plate would be lost due to sulfation. So when we're trying to determine if sulfation is an issue, the quick steps in order to do so, going back to measuring and recording specific gravities, what you will see in the case of sulfation is you'll see a battery bank with very equal specific gravities but are all very low. Put the bank on charge. If the battery is heavily sulfated or if sulfation is an issue, you'll notice that the bulk voltage is attained very quickly and then all of a sudden current starts to drop. So you'll measure and record the specific gravities again. All will remain low. And the reason they'll remain low is because a lot of current has not been accepted. And the only solution in this case is to now equalize the battery bank. A proactive measure after this would, of course, be to go back and probably extend the absorb time or increase the frequencies of equalizations. So some preventative measures: record the specific gravities, observe the trends. Are specific gravities starting to tail off? In hybrid systems with generator backup, where PV production starts to tail off this time of year and then gets to it gets to its low later on in the winter, you probably see maybe specific gravity readings starting to tail off during that period of time, unless generator runtime starts to obviously increase to offset. And if the absorb time is not set correctly when we're running generator time, of course, No one's going to run a generator in float to finish off. So if the absorb time is not set correctly, then we're going to have difficulty getting the battery bank fully charged without doing more frequent equalizations. The key to sulfation is this last line, is that the battery bank can be brought to 100% state of charge every month. Difficulties with sulfation don't exist, and the requirements of equalization really don't, equalization isn't required either, because the battery bank has been brought to 100%. If it's brought to 100% every month, you may need to do an annual or biannual equalization just to balance out voltages.
Hi, Jamie. Just to clarify on charging, we've got a question here. You're saying the size the correct charger for a bank, you need to calculate 20% of the 20-hour rate and then add a 15% inefficiency.
Yeah.
Inefficiency buffer.
Correct. We'll just go back to that slide. To calculate the required amp hour, which is going to have to be created, we know when in a healthy battery bank, when bulk voltage is reached, the battery is still 20% discharged, or it's reached 80% state of charge. So 20% of whatever the size of the battery bank at the 20-hour rate is the required amp hours that we need to create. But if we only created those 20%, they're obviously not going to make their way into the battery. So we need to increase our number by at least 15% to compensate for the inefficiency of both the battery, loss due to heat, loss due to line loss, etc. And that will give us the amount of amp hours that need to be created. And then to determine the absorb time, we just need to divide those created the required ampere hours by the charge rate. Now the charge rate is the one sticky part here, because now we need to estimate the amount of current that's going into the battery during an absorb time. And again, if you don't have an idea, take 50% of the output of the charger. If you have an 80 amp charger, assume that 40 amps is all that's going to go into the battery during the absorb phase. And again, I'll just back up and show how the current tapers off once bulk voltage is achieved.
And Jamie, what about the bulk current? I think that's particularly what they're asking. So on a brand new bank,
okay, bulk current, the battery can accept, maximum acceptance is going to be in the area of 20% of the 20-hour rate. So if we have a battery bank,
add 15%?
No. The acceptance rate during bulk charging is 20% approximately of the 20-hour rate of the battery, which has nothing to do, of course, with the absorb stage. The battery bank, if you put in a 1,000 ampere hour battery bank, what it's saying is the maximum that bank is going to be able to accept when it's fully discharged is 20%, which is going to be 200 ampere hours. So therefore, approximately 200 amp hours would go into that battery bank, drive the voltage up to bulk voltage. Once bulk voltage was attained, that current is going to start to drop off. The question becomes, how quickly does it drop over the absorb stage? My rule of thumb that I'm providing is if it's accepting 200 ampere hours at peak maximum acceptance, the absorb stage acceptance is going to be roughly 50% of that. And that is what you can use in order to determine how long the absorb cycle needs to be. Is that clear?
Yes, I think that's good, Jamie. Thank you.
Okay. Again, the same calculations used when we try to determine how long we need to equalize a bank for during a corrective equalization. So we've gone through, we've troubleshooted, we've determined that the specific gravities are all low in the batteries, the voltage is rising quickly, we don't have a bad cell, we have sulfation, Okay, so how long is it going to take to bring this battery bank back? So let's say we're looking at a 1,000 ampere-hour battery bank. We determined, again, that the battery is roughly 80% charged, or we need to create or replace 20%. So we need to replace 200 ampere-hours. Again, creating 200 amp-hours will not replace 200 ampere-hours into the battery bank due to losses as a result of inefficiency. So let's increase that by 15%. So we increase that by 15%. Now we know we have to create 230 ampere-hours. Again, we just need to determine what is going to be the charge rate. All I've used here is 5%. Now, it's not that the battery will only accept 5%, but normally during heavily sulfated batteries, the charge acceptance rate is quite low. So this will give a good idea of how long it would take to bring the battery bank to full charge. 1,000 ampere-hour battery bank charging at 50 amps. We're going to need to charge for roughly 4.6 hours. The only limiting factor when doing equalizations is heat. We don't want the electrolyte in the battery to get hotter than 125 degrees Fahrenheit. If the battery bank starts to approach those temperatures, we have to shut the charge current down, let the battery banks cool, and then repeat the process. Other factors that can be a concern, of course, is if we had a bad cell. So how do we determine if we have a bad cell? Again, we're going back to measuring and recording both voltage and specific gravity. If you put the bank on charge, you measure and record specific gravities and voltages again, you'll notice traditionally with a bad cell, one cell will not have, there'll be excessive water loss in all the cells but one. There'll be very little or no activity, no bubbling, no reaction going on in one cell. And that is undoubtedly going to be the cell that has gone bad, the one that has no activity. And if you measure the voltage, definitely under load, the voltage is going to be significantly lower in that cell. If you're measuring specific gravity and you see one cell has greater than 30 points, so all of the batteries or cells are 1265 and it's 1235, it's definitely a concern. It does not mean that that cell is bad at that point in time, but it definitely means it should be looked at. Why is it lagging behind so far? Now, it is possible maybe it's received more water, maybe it was partially discharged on install, who knows? But you should definitely mark and make a note to check that cell quite frequently to see if it's coming back or falling off further. In the case that you've determined that there is a bad cell, that cell or battery needs to be replaced, and then the initial activation procedure should be done as if it's a brand new bank, i.e. put the new battery into the bank and run a relatively high voltage charge for a couple of hours to make sure that the entire bank is married in and all at full charge before you start discharging again. But what happens in the case of overcharging? Again, just trying to show some actual visual indications of what will happen. If you take a look at the plate on the left, this plate, the active material is gone to become a very typical soft oxide that happens when a battery has been cycled till the end of its useful life. And physically, it's called soft oxide or sponge oxide, sponge lead, because it physically takes on it's very soft when you squeeze it, where initially it's rock hard. But if we take the picture on the right, this is a cell. It's almost sad to look at. It's been absolutely destroyed. And it's destroyed to the point that all the active material has been essentially pushed off the plate and grid metal is showing. This is chronic overcharging and just abusive use on the battery. So I'll quickly now just kind of take a quick run through our product lines and also note some of the new products we have on offer. But essentially, our products make up two series. On the flooded lead acid side, we have the Series 4000 and the Series 5000. The 4000 is made up of typically L16s as our primary movers, be it the S460 and 530 being the most popular models. Good product, good cycle life for the size of the battery, has a good warranty, a 7-year warranty. The only downside would be, or I guess a recommendation we would make would be, 2 strings in parallel would be the maximum size of bank that should be used. Saying 1,060 ampere hour, which would be the case of 2 S530s, but we also have the S600, which would mean really we could go to 1,200 ampere hour at 48 volts. Once the battery bank requirements get larger than that, you should move to larger batteries. The most efficient battery bank is a single series string comprised of cells at the capacity that you require. So if you require 1,200 ampere hour at the 20-hour rate, get 1,200 ampere hour cells and build them up until you reach the voltage that you require, 24 volt, 48, what have you. The features, benefits, competitively priced, it's well recognized, good cycle life, great liquid reserve, great warranty. But the downsides are it's very easy to cost compare. So an L16 becomes an L16, which makes it very difficult for resellers like yourself to get a premium price for a product that hopefully you believe is premium because it's the same physical size as other product on the market. And also, far too many of them are often used. I've seen battery banks where in excess of 48 L16s are being used, and it's just a spaghetti factory with multiple cells that are never going to be checked, they're never going to be maintained. And as you start adding parallel strings, of course, now you start increasing the requirement for equalizations to balance out the bank, and it can become nightmarish. The other series is the Series 5000, and I guess I'll just preface this. I don't mean to suggest the Series 4000 is a good product. If you need an L16 or similar size, I think they're very well built and they do a very good job. The problem is just they get used too many of them get used to create high-capacity battery banks. If you need high capacity, this is where the Series 5000 comes in. Everything is manufactured in the Series 5000 with a dual container, so it has a removable cover, a removable outer case, and it's modular design. So all the cells are bolted together. In the case of the 4 and 6 and 8 volt and 12 volt systems. We also make a 2 volt, which would be, or a few 2 volts, which would be just single 2 volt cells in the plastic case. The advantage, larger cells, larger capacity, means more liquid reserve, and it also means higher cycle life. So they're just going to last longer. Unlike steel tray batteries, which would be the traditional competition we would go against in these sizes, the dual container prevents, as a result of the removable cover, it eliminates the tops of the cells from getting dirty and wet over the use. So what happens is we eliminate the stray current and stray voltage that builds up as a result of dirt and crud being on the top of your battery. Traditionally in steel tray batteries, the cells are obviously exposed, they become dirty, they become wet. Moreover, you risk the possibility of having voltage to ground as a result of the steel tray. Give you up to 20-year operational life, and as I already mentioned, very high cycles. Some of the limitations of this product, again, higher upfront cost, larger and unfamiliar sizes. So they're harder to move, and they're not known by everyone. Overall, I guess this is, again, I apologize, I guess I'm really beating the stump speech here, but very broad, flooded product, good warranty, good cycles, some unique features like the dual container. I only mentioned in passing, but all of our cells, both the L16 and the larger, are cast on strapped, which means that they are burnt inverted, which means that we eliminate lead runs. The larger Series 5000 are all burnt robotically. All the wet product is load tested before shipping, and all the Series 5000 is actually capacity tested as well. And I think we support our distributors quite well and have been doing so since a long time. Now quickly, just onto some new models. The 2YS31 actually isn't particularly new. There's quite a few out there, and they've been in distribution for a period of time now. But it is still new to several people. It's our highest capacity cell that we're manufacturing, so 2,400 ampere hour at the 20-hour rate, or 3,400 at the 100-hour rate. It's a large cell, but when this sort of capacity is required, it allows us to go into a single series string. And if that's not big enough, we actually have the 2YS62 in development. which will allow us to double the capacity up to 4,800 ampere hour at the 20-hour rate, 6,800 ampere hour at the 100. But this is going to be a monster. And again, we're looking at having this into production the early part of 2010. We have an S1380, which is a very interesting product and has actually been very successful. It's an individual 2-volt cell in an L16 format. All it is our very popular S460, but instead of being burnt as 3 groups, it's burnt, all the plates are burnt as 1 cell. And so now we're able to get 1,000 ampere hour in an L16 format without having to go into multiple parallel strings. So we can go into a series string, increase charge efficiency, decrease the number of cells that have to be maintained, decrease the number of connections that have to be maintained. Also, as you can see, it has a very large connecting strap. The reason we've done that is now we've moved up to a 1,000 ampere hour cell. We actually have to go to what's called a 4-post cover. So both the positive has 2 posts, the negative has 2 posts. That doesn't mean there's 2 connection points. There's only 1 connection point, but they're burnt together in a common terminal. The reason we've gone to a 4-post cover, again 2 positives, 2 negatives, is so that it can maintain or actually support the potential loads that you can put on this battery. If you think of it, you can easily discharge a 1,000 ampere hour battery at 200-300 amps, and a single post may not be able to support these types of loads. These are in production and are shipping. And we're actually working on the S1590, which is the S530 equivalent of this, and it'll also be shipping in early 2010. The S600, which is a higher capacity L16, the highest capacity we manufacture at this point in time, 450 ampere hour at the 20-hour rate. We've just been able to squeeze in 1 more plate pair into the same size group, same size container, so it's the highest capacity. Now we have 3 L16s, the 460, 530, and 600, and it is shipping as well. As mentioned earlier, we've been beta testing the FC420, which is a flooded calcium L16. The whole intention of going calcium, we eliminate the antimony from the grid metal, which gives it the benefits of low discharge rates, low off-gassing, similar to an AGM or a gel, but because it's flooded, it has the added robustness of a flooded cell as well. Works very well in grid-tied systems. We've had them in 15 sites worldwide, and all of the sites all of the sites except 1 have performed exceptionally well. No water added, well over a year, etc. in float service. But one site's been reporting some very weird data, but they've also had these heavily cycling use. So the point of all this is we're very confident for float service, grid-tied systems with battery backup that work very well as an economical solution to get higher capacity in these grid-tied systems without having to go sealed. But,
Jimmy,
go ahead.
Quick question. Someone's asking about the self-discharge rates. For example, if throughout the winter you were shutting down a cottage or something and you wanted to keep a trickle charge going into batteries, what current would you need to keep the batteries from self-discharging?
If it's a cottage system or a winter system, obviously the ambient temperature of the battery bank is going to drop. When the ambient temperature of the batteries approaches somewhere around 4 degrees C, the self-discharge rate goes to 0. And the freezing temperature for 1265 acid is some stupidly obscene minus, 60 degrees Celsius or something like that. So the point of all this is fully charged flooded cell batteries won't freeze. So we don't really have to worry about the self-discharge rate. Now, if there's a load on the system, of course we have to offset that load. Or if we put the battery bank away in freezing temperatures partially discharged, of course if it's fully discharged it's going to freeze at 0 degrees C because the electrolyte, or very close to, because the electrolytes approach water. But at fully discharged we don't have any concerns, and even partially down to 50%, well, 40% depth of discharge, 60% charged, even in our winters, we're not going to probably freeze that battery. So all that to say, it doesn't require much current at all to maintain. It actually requires no current if the batteries are in a very cold environment. As they approach warmer temperatures, so at 25 degrees C, you know, a battery bank may discharge somewhere in the area. I think at 40 degrees C, it's 30% a month, you know, 1% a day. At 25, it's somewhere around 15% a month. So if the battery banks are in a warm enclosure, then the amount of current that has to go in the battery banks is higher. I don't know if that's answered the question or not, but I'll await confirmation.
Yes, thanks.
Okay. So we're mentioning the FC420, which was the flooded calcium, great for grid-tied standby systems. However, it's not a sealed battery, and sealed batteries are required, so we do have an AGM product on offer. It's a relatively tight range. We have 9 monoblock sizes, so ranging from 885 to 415 ampere hour in both 6 and 12 volt configurations. And we also have 6 2-volt cells from 550 to 3300 ampere hour. And all of this product is available and is shipping. And just some quick, and this is all available online, but you know your voltage settings. If you look at our our recommended voltage settings versus a lot of the product on, we're going a bit more aggressively. And the reason being is traditionally the AGM product voltage recommendations are quite low in order to make sure that the battery is okay long term. But you can actually push the batteries, if they're well made, significantly higher than the recommendation. So if we kind of take a look at the 25C, which is the traditional, we'd be looking at somewhere between around 14.7 volts on a 12-volt system would be the recommended voltage, which is a couple of tenths of a volt higher, or a tenth of a volt higher than a lot. And the batteries can support that. And as a result of the AGM technology, it's a calcium grid, the same as the FC420. You've eliminated the antimony, so you have a significantly reduced self-discharge rate. So at approximately 20 to 30 degrees C, these batteries can sit for 6 months without having any concerns for a refresh charge. And just to confuse you with a whole pile of numbers and graphs, just taking a look, because it's an AGM chemistry, it has a lower internal resistance. The charge acceptance is actually higher. It can accept 25% at C20. You can even push it a little bit higher than that, but let's just stick with 25% at C20. And you're going to be looking at an absorbed voltage at 2.45 volts per cell. And as you can see, the temperature coefficient is going to be based on 25 degrees C, of course, minus 4 millivolts per degree C. And that is the, float voltage of 2.3 volts per cell. We also have just a set of new level indicators. We have a Series 4000 that works on all the L16s and a Series 5000 that works on all the dual containers. I'm just going to skip over the recombination caps, but they're still not available, and poor HES has seen this slide several times. We're in final testing with the Recombi cap. We're hoping to be able to ship this before the end of 2009. And it's an actual recombination cap with an internal catalyst that can recombine the off gases and put it back as water, extending lead time or extending watering intervals to 365 days on a flooded product. And then finally, we also have the terminal boots available for all the Series 5000, which just finishes off the install. And I'll close with just a few installed examples, which won't be a surprise to many of you. I think all of these are married to Outback systems, which is not intentional. And this is one that we'd like to show, which is a solar panel fabrication plant in Veracruz, Mexico, that is operating a 240 volt AC, 240 volt DC system. 440 volt, 240 of these 2KS33s, in series for 440 volts. And they run the entire plant off these batteries from approximately 10 o'clock in the morning till 5 o'clock at night. The first few hours of production, they run off a large genset so they get the laminators hot and so forth. And I believe that's it. If there's any questions, feel free to ask.
Thank you, Jamie. Really appreciate your presentation there. And if there are any questions, feel free to type them in right now and we'll post them for you. I would also like to take this time to invite everybody to join Surrette and Home Energy at the CAMSIA Solar Conference this December 7th and 8th. We'll be there with some booths, and I believe that Surrette will be joining us there. That's correct, isn't it, Jamie?
I believe so. It's in my calendar.
Excellent. And if there's not too many questions right here.
That's fine.
So thank you very much, Jamie, and
thanks again, gents.
Any further development?
Thanks,
Appreciate
Jamie.
it. Bye.